Are you able to see my screen?
Yes, sir.
And I am audible, na? Clear audible?
Yes, sir.
Okay, so this is what problem we have solved. So what we have seen is viscosity. Now, actually, you will see actually as we have discussed initial classes. Initial classes, what we have discussed is there is a close correlation between heat transfer, mass transfer, and momentum transfer. So generally, you will see that now I will give more attention to one area only. So remaining area will be kind of self work or take home assignment kind of thing. So similarly, I am spending more time with viscosity. So same line on same line. So you can discuss diffusivity also. You can discuss thermal conductivity also, and that briefly I will cover maybe in one class or couple of classes, and almost three classes we are discussing this viscosity. So what we are discussing viscosity is first empirical graph we have discussed. So empirical graph, how to use empirical graph. So if you have reduced pressure, reduced temperature, so you can get a reduced viscosity. And if you are able to get reduce critical viscosity, certainly you can get the viscosity. That is what the empirical graph is there. Then we have Maxwell early equation, you can say. Maxwell early equation tells so he has assumed that okay, so kinetic theory of gases and low density gases where molecules are assumed to be a spherical particle with negligible interacting forces. So with that he has derived this Maxwell initial equation, and then when computations, and this is Maxwell early equation. This is Maxwell early equation. So then when computation and everything is developed, so that time people have tried to simulate okay molecules, and that time they have correlated this viscosity some of the constant like collision diameter and collision integral. These are the constant from you can say the statistical thermodynamics and molecular dynamics simulation. So and this is Maxwell equation, so this data is also available, so using which we can get the viscosity of gases. Okay, then this is how we can get the viscosity of mixture of gases. If I have mixture of gases, so one way is simply I can use this formula, only this. So neglecting this, phi alpha beta equals to 1. So if you phi alpha beta equals to 1, so interacting forces are same for all. So this will reduce to this equation only. That also can be used, but that will give you a crude value, and this is more so this dimensional quantity phi alpha beta is kind of an interaction. Okay, interaction, viscous interaction between alpha particle and beta molecule, alpha beta molecule. So you can get the interaction. So this problem we have solved in last class. So you can get the interaction, you can get the summation, and then you can get into a viscosity of mixture. This is what we have seen till now. So anybody has any confusion over here? Okay, then what we will now we are going to see is molecular theory for viscosity of liquids. Okay, this is the equation which is the combination of Avogadro's, Planck, and some other observations also. So mu equals to NH divided by V. So N is Avogadro's number in gram mole per inverse. Okay, so Avogadro's number, you know, these are the number of molecules per gram mole of the compound. Number of molecules per gram mole of the compound, that is Avogadro's number. So V is a specific volume actually, volume of the moles of the liquid, centimeter cube per gram mole at a given temperature. What is the volume of moles of liquid in centimeter cube per gram mole? As I am telling, this is also empirical relation. So this is very very clear. So people have correlated boiling point with a viscosity. This is actually nobody can think that okay theoretically boiling can point can be correlated with the viscosity. This is only can happen in empirical equation only. So you can see boiling point. there is nothing to do with boiling point and viscosity of liquid. Still, they got a good correlation that this given correlation. So where Avogadro's numbers are used, Planck constants are used, and they try to fit this viscosity at different temperature. They got good fit, and this is the equation we can use for estimation of viscosity of liquid. So N is a Avogadro's number, H is a Planck constant, V is a specific volume per gram mole, mu is a viscosity in gram centimeter per second, and TB is a normal boiling point in Kelvin. So here, so in all the calculation in engineering, so most of the time this temperature will be used in Kelvin, because whatever this model equation developed, these are in US or European country, their common units are Kelvin for temperature. So if you make a mistake here, instead of Kelvin, if you use degree Celsius, and there is a ratio, actually this ratio will have different value. Okay, even though this is temperature, you can use, if it is say mass or everything, anything, you can use anything, lb or gram or anything ratio. All the that will be this you can say conversion will be nullified, but in temperature it will not happen. So you need to make extra efforts, or extra caution should be given whenever you are using temperature anywhere in engineering calculation. If temperature you are using, even though it is ratio of temperature, so you should make sure that what should be the unit of that temperature should be used. So here boiling point is used in Kelvin. So this is in a form of, okay, so mu a into exponential of b by t, and many people have used this exponential also, and you will find n number of equations for various liquids. Okay, because liquids also, there are different types of liquids. Okay, so different types, in a sense, some is viscous, some is say Newtonian, non-Newtonian. So you will find different value of A and B for category of liquid, actually different category of liquid. So this expression and this expression are same, and this is also one of the commonly used expression with you. If you go to particular data books, so you will get this constant value of A and B. So A and B, and here they have elaborated. So A will be equals to Avogadro's number into Planck's constant divided by volume, specific volume, volume per unit moles, and B equals to 3.8 into boiling point in Kelvin, and T is in Kelvin. So this is what you can use, okay, for estimation of liquids. Again, we are doing same thing. This can be derived from molecular theory of viscosity of gases. Plus, here actually you need additional knowledge of thermodynamics also. Thermodynamics is deeply involved. So we are not interested in deriving this equation, okay, deriving this equation or background of the equation. We will just use this equation. Is it okay? Are you able to hear me?
Yes, sir.
Yes, sir.
Okay. So, can you see the problem?
Yes, sir.
Okay. Can you just try to solve this problem? So, estimate the viscosity of liquid benzene at 20 degrees Celsius. So you need a following information: boiling point of the liquid and the molar volume of liquid. Okay. So what is the molar volume of liquid? So this data you can obtain. from various data book. So I think it is in degree Celsius here. So what I have told you, that is the only, you can say, point of concern, that you convert this temperature in Kelvin first. Okay, this is given in Kelvin, 20 degrees Celsius. You convert this boiling point also in Kelvin, and remaining you can use this. Specific volume is in centimeter cube per gram mole. Here it is given in centimeter cube, and these are the Planck's constant. So Planck's constant is in erg per second. So you will have Planck's constant. This is in joule per second, and this is in erg per second. So you need to use in erg per second. So even though you can see there is a order of magnitude variation, okay. So even though if you make a mistake, if you think that okay, Kelvin is in SI unit, so I will use this Planck constant in joule per second. That is not that will not be correct. So you need to use in erg per second. So 6.62608 into 10 raised to minus 3, and this Avogadro's number is gram mole inverse. Yeah, this is okay. So you can use this molecules per gram mole. Number of molecules. This is Avogadro's number indicates what is the number of molecules in 1 gram mole of any compound. This is true for any compound. 1 gram mole of compound will have 6.02214 into 10 raised to 23 molecules per gram mole. This is Avogadro's number. And temperature is given at 20 degrees Celsius. Boiling point is 80 degrees Celsius. So what will be the viscosity of benzene? So anybody got the answer?
Sir, it is coming 4.36 into 10 to the power minus 3 gram per centimeter second.
Very good. So very easy actually. Convert this temperature in Kelvin. Okay. So this is what all the data is there. So only the thing is you need to convert this temperature in Kelvin and substitute all the values. So this is what the equation will be. So this is 4.5. This is what you got. Yeah, almost everybody is getting 4.3 into 10 raised to minus 3 gram centimeter per second. Yeah. Yeah, everybody got this. Okay, this is kind of 4.5 into 10 raised to minus 5 Pascal second. Yeah, SI unit. Okay, or you can write this millipascal. This gem stands for milli. So 0.45 millipascal second. So this milli 10 raised to minus 3 is removed, and this one digit. So 0.45 millipascal per second. So this is how you can estimate the viscosity of liquids also. And as I am telling that, okay, this is true for engineering correlation also, estimation of heat transfer coefficient, mass transfer coefficient, and friction factor. So this continuously there will be development in this area. Okay, because these are empirical relations. So certainly there will be limitations of this. Okay, limitations of this. This is applied for Newtonian fluid only. So many limitations will be there. So you can go in details in books. So all the limitation will be listed. So you cannot use this universal. So certainly for limiting cases, people will study and give the appropriate engineering correlation, and then you will get a new equation day by day. So in literature, you will find n number of equation for this estimation of transport property in a sense. Transport property in a sense, viscosity, thermal conductivity, diffusivity, then heat transfer coefficient, mass transfer coefficient, and friction factor. So you will find many equations. Okay, that is what you need to remember. So most of the time, whatever case you are studying or whatever case you are designing, certainly there will be some empirical correlation available to get this transport property. If it is not there, then you need to do the experiment in lab. You need to do the experiment in lab and try to get the equation in the form of dimensionless number, and that equation can be extrapolated for industrial this scale up also, industrial scale up. That is what you can do in future if somewhere needed and you are not getting at all any engineering correlation. So you are search everywhere, all the heat transfer book, mass transfer book, momentum transfer book, and transport phenomena book. You are search everywhere, and you are not getting the engineering correlation required for your case. So what you can do is you need to design the experiment on lab level, convert that information. Okay, do the experiment, convert that information, get the empirical relation in terms of dimensionless number, and then you can scale up. So that is the importance of dimensionless number. Whenever this expression is given in dimensionless number, so it is very easy to extrapolate the information on or scale for scale up. You can easily use that information for scale up. Okay, so now viscosity of suspension. So emulsion and suspension is there. So effective viscosity, this is the effective viscosity you can calculate. Mu zero is the viscosity of suspending medium. Okay, so say there will be some suspension also which will behave non-Newtonically. So just if you know the viscosity of suspending medium, say if you have this thing, what can be there actually? So water and say, can you give me any one example of suspension and emulsion? Any one example from class? Can be a toothpaste. Okay, so there will be some base fluid in which all solids are suspended, even though that will be very thick actually. So kind of that only, suspension and emulsion. So if you know a suspending medium, say everything is dissolved or suspended in a ethanol. So this will be a viscosity of ethanol, and this will be the volume fraction of sphere. And this is true for low concentration. Not that is wrong example. So this paste and all. This is true for lower volume concentration of sphere. So you can calculate the viscosity of suspension also. Okay, this is just for information. So you can use the data for getting the viscosity of suspension wherever it is used. So this is very important. So nowadays people are trying this using some nanoparticle in a coolant in a vehicle. So coolant in a vehicle previously is a pure compound. Now people are using nanoparticles in low concentration, and certainly there will be a flow of coolant. Flow of coolant means viscosity will play a role in designing purpose. So viscosity will flow. So that time, so that coolant with a nanoparticle viscosity can be estimated by using this equation. So mu effective will be equals to mu zero equals to 1 plus 2 by 5, and generally volume fraction of this nanoparticle in coolant will be lower, less than 1%, less than 2%. That time this will work very effectively actually. So this is how we can get the viscosity of suspension and emulsion. Now thermal conductivity. As just starting of this class, I will briefly explain. So there is an empirical graph, then Maxwell equation, then Maxwell advanced equation, and you can estimate the viscosity. And viscosity is similar to thermal conductivity. So viscosity is similar to thermal conductivity. Certainly. So in literature, people have studied thermal conductivity is also on same line. You can see thermal conductivity also studied in same line. So in that, what will be the first step actually you can expect? Here, roll number 18, Ashish.
Yes, sir.
So, what is your expectation? How you can get a thermal conductivity?
Sir, like it's a property of any material. So sir, uh, in
Yeah,
either we get it experimentally, or if we have to apply any.
no, how you got viscosity
Yes,
first in first part actually.
sir. using various experiments or rely on experimental data
Yeah,
or
experimental data are compiled and put in the form of.
or sir, we can do by pressure do by like pressure or temperature also depends on temperature and pressure, like how
Yeah,
it
yeah, yeah. But what we have done, how you got viscosity first time actually, low density gases and all, or before
sir,
that we got actually one that I told the empirical
like
graph.
sir, we derived we get a formula like 2 by 3 root mkt by pi, that one, like for
Yeah,
viscosity.
before that we have used empirical graph.
Yes sir.
So
Yes
that
sir.
certainly,
Yes sir. Oh, yeah, yes sir, that
so
empirical
that
graph.
is also empirical graph. So
Yes
what
sir.
do you mean by empirical means? That is compilation of large number of data in the form of graphical
Yes sir.
representation, empirical graph. So it is not a experimental graph purely, or it is not a theoretically derived graph. Actually, that is empirical. Empirical means
uh,
part of
yes
experiment,
sir,
part
which
of
is like which is
theory.
like a compilation of large experiments and rely
So
on that.
certainly on same line you will get an empirical graph for thermal conductivity also. What
Yes
is
sir.
your expectation, Ashish, on x-axis, y-axis?
So
So that is what very important actually. Even though first 10 classes of this transport phenomena uh, was just
sir,
an introduction to
temperature,
this transport. Huh?
temperature and that kinetics.
Temperature and
Yeah.
kinetics.
No, like sir, why x-axis might be a temperature because it depends on temperature,
Very good.
reduced temperature, and uh, sir, and y-axis maybe reduced K or vis,
Reduced K means what is there?
thermal conductivity.
Yeah, reduce thermal conductivity. Okay, so
Like
this
it
is
is
what the
same
graph
as
is there. Okay, this is what graph exactly similar. So it was exactly similar graph. So there I have reduced temperature versus reduced viscosity previously. Now here you can see I have reduced temperature versus reduced thermal conductivity at different value of reduced pressure. Okay, at different value of reduced pressure. So certainly, so this you can appropriately judge the range. Okay, range of, say, you can get a reduced temperature up to 10. Okay, this is logarithmic scale 10, and reduced pressure up to 40. So what is the state of material up to that? Okay, that only you can get the viscosity, thermal conductivity using this graph. That will give the limitation. So now you can see here also previously this PR is nothing but pressure divided by critical pressure. PR is a pressure divided by critical pressure, and this already we have explained. We got input related to this in our previous that first time. So now here I have six properties. So reduced temperature have temperature divided by critical temperature. Reduced thermal conductivity will have thermal conductivity divided by critical thermal conductivity. And this actually reduced pressure will have pressure divided by critical pressure. Out of 6, if 5 are known, then certainly I can get the value of 6. So out of this 6, this critical temperature you can get it from data book, critical pressure you can get it from data book, critical thermal conductivity you can get it from data book. If say pressure and temperature is given, you can get the value of thermal conductivity. Temperature and thermal conductivity is given, you can get the value of pressure. Pressure and thermal conductivity is given, you can get the corresponding value of temperature. So this is how you can use this empirical graph. So out of these six properties, five properties should be given. Out of this five property, three properties can be obtained from data book. If two properties are given, I can estimate third parameter values from this empirical graph. Exactly same we have done in in case of viscosity also. Okay, so you can see similarity. So that here comes the importance of our first 10 classes, where we have tried to justify thermal conductivity is similar to viscosity. Thermal conductivity is similar to viscosity, then certainly we'll get the confidence, because already I have used a similar graph. So similar graph in viscosity, similar graph is available in thermal conductivity, similar graph is available in diffusivity also. So what might be there on in diffusivity, in case of diffusivity? So this empirical graph, roll number 37, Vignesh.
Yes, sir.
So what will be there? Similar empirical graph in mass transfer.
Sir, in mass transfer, it might be on x-axis,
X-axis.
velocity,
Mass
and
transfer, I am telling.
sorry, concentration, sir.
X-axis.
dc by dA. Sir, on y-axis it might be concentration, and on x-axis it might be.
Yeah, you want very much deep details in transport phenomena actually. Everywhere you are changing. So now two examples are given. Yeah, Deepshika, roll number 54.
Yes, sir. Sir, on the x-axis, it will be reduced temperature, and on the y-axis, it will be reduced diffusion.
Yeah, very good. So for different value of reduced pressure, for different value of reduced pressure. So on x-axis it will be a reduced temperature. On y-axis it will be reduced pressure. Not y-axis, it will be reduced diffusivity for different value of reduced pressure. So you will get this relation. Okay, in mass transfer. So anyway, we'll solve some of the problem based on this. So this actually estimate the thermal conductivity of ethane at 153 degree Fahrenheit, and this thing is 191 atmosphere from the experimental value of K. Uh, Thermal conductivity is given at 1 atmosphere and this temperature. So thermal conductivity is given at 1 temperature and pressure. So what will be the value of thermal conductivity of another temperature and pressure? Temperature remains constant, pressure is only changing. And I want to use this graph. So how to solve this problem? Roll number 75.
Yes, sir.
Yeah, how to solve this problem? Now, as I told, there are 6 property involved here. Pressure means, reduced pressure means pressure divided by critical pressure. Temperature means temperature divided by critical temperature. And this thermal conductivity means thermal conductivity divided by critical thermal conductivity. Now, temperature pressure is given, and thermal conductivity is given. One thermal conductivity is given. So I want to estimate the thermal conductivity at another temperature and pressure.
So first I need to calculate the uh, reduced values of
Yeah,
temperature.
reduced value. For that, you can get the from data book ethane. For ethane, you can get a reduced temperature and reduced pressure. So you can get a reduced temperature and reduced pressure. Then
Uh, so then using the graph, we can get the value.
using the graph, you can get, first of all, using this value and graph, empirical graph, you can get a critical thermal conductivity value, and use that critical thermal conductivity value to get the thermal conductivity at this temperature and pressure.
Yes,
Is
sir.
it okay? So you can see actually here, ethane. Where is ethane? Rule number 92, Saransh. 92, 94 Saransh.
Yes, sir.
Yeah. So what are the values of ethane?
Uh, Sir, for ethane, molecular weight is given in the table as 30.07. And we need TC and PC. So those are given as 305.4 Kelvin and 48.2 ATM.
This is correct.
Yes, sir, these are the critical properties. So then now we can calculate the reduced properties from here.
So C2H6 is the ethane.
Yes, sir.
Okay. Correct, na? Are you
Yes,
sure?
sir. Yes, sir.
Okay. Okay. So this is the molecular mass of ethane. Okay. This data currently not used. So you use critical temperature, critical pressure, and this value of thermal conductivity. Get the value of critical thermal conductivity, and then you use this temperature, this pressure, use this TC, this PC to get the value of thermal conductivity at 153 degree Fahrenheit and 191 atmosphere. So certainly you need to convert this temperature in Kelvin. Okay, you need to convert this temperature in Kelvin. This is repeatedly I am telling that whenever you are using any design equation, either in kinetics, thermodynamics, heat transfer, mass transfer, anywhere, so you make sure twice. So what is the unit of thermal temperature you are supposed to use, and what is the unit of temperature it is given in a given data. So because this is here only this generally people will make a mistake, and that mistake will give you altogether different answer. So you start with this. So reduce pressure. Roll number 1, Abhinav.
Yes, sir.
What is the value of reduced pressure and reduced temperature?
Uh, Sir, reduced pressure is 0.022.
0.022. And what is reduced temperature?
Yes, sir. Sir, it is 1.12.
1.12. So this is you can say this is the temperature conversion actually. This is temperature conversion. Some 9/2 something will be there. Okay. So this is 153, and this is 305.4. 305.4, and this is the reduced pressure. Everybody is getting this reduced temperature 1.115 or 1.12 something, and reduced pressure 0.002. So what hereafter? Roll number 26, Vijit. Roll number 35, Pranit.
Hello.
Yeah, what need to be done hereafter? For this temperature and for this pressure, we got reduced temperature and reduced pressure.
So like from graph, we can find reduced thermal conductivity. Yeah.
Very good. Thereafter,
Since K value is given, we can find Kc.
Kc. Yeah, very good. So from here, so this is pressure is somewhere close to zero. This is pressure. This line indicates reduced pressure equals to zero. Okay, this line indicates reduced pressure equals to zero. So 0.002 will be very close to this, and reduced temperature is 1.11. So somewhere here. So here somewhere you will get a reduced thermal conductivity. So in exam and all, you can go with scale and everything. So you can extrapolate this. So somewhere here, so this is 1.1 somewhere. This is logarithmic scale. So 1.1, and here close to this. So somewhere here I will get a reduced value of thermal conductivity. So it's 0.36 is given actually. So 0.36 means close to here actually somewhere. Okay. So this is the point. So reduced value of thermal conductivity at this point is 0.36. Hence, you can get the value of Kc. What will be the value of Kc? Here, roll number 32.
Yes, sir. It's we divided K by KR reduced value and
Uh,
0.0442, sir.
what is the unit?
So BTU per hour feet per night.
Yeah, very good. Okay, because I'm using this value actually here. Okay, so whatever this unit will be the unit of this thermal conductivity here. So here you can make sure that okay, temperature and everything accordingly converted. Okay, so you can get this 0.0442 BTU hour per feet degree Fahrenheit. Now use this is the critical value of thermal conductivity. Now I want a thermal conductivity at this temperature and at this pressure. So temperature remains same, only pressure is changing, 191 atmosphere. So what will be the reduced value of temperature here? It will be 115 only. What will be reduced value of pressure here for this 191 atmosphere? Here roll number 61 to tweak.
Yes, sir.
What will be reduced value of pressure
Pressure.
at which I want a thermal conductivity?
Sir, we want the thermal conductivity at 191.1 atm. So that for that we will find the reduced pressure value 3.98.
3.98.
9.
Okay, so this is 3.98 something. Now I will go again to graph. Okay, so temperature is same, 1.1. So vertical axis will be same, only horizontal axis will be changing. So I will be following same line which we have followed. Somewhere here it was. So I will follow and go to 3.2.9, 3.9 or 2.9. It is 2.9 or 3.9. It is 3.9. So somewhere here it should be there actually. So I will get a reduced value of thermal conductivity. So it is 2.07. So 2.07. So somewhere here actually 2.9. So somewhere here actually it will have. So 2 point something will be there. So you will get a reduced value, and using this and critical value of thermal conductivity, I can get the thermal conductivity at this pressure. So what is the thermal conductivity at this pressure, 191 atmosphere? Roll number 62, Ramaya Shri.
Yes, sir.
So what is the thermal conductivity at 191 atmosphere?
I got 0.091 BTU per hour feet Fahrenheit.
Yeah. So now here also same thing. So I have 6 parameter in this empirical graph and a empirical graph. Empirical graph is given and there are 6 parameter. What are these 6 parameter? Temperature, critical temperature, pressure, critical pressure, thermal conductivity, critical thermal conductivity. Out of these 6 parameter, 5 should be given, so I can estimate 6th one. So certainly this you can get critical temperature, you can get critical pressure, even you can get a critical thermal conductivity is also from data book. Okay, from data book you can get a critical thermal conductivity also. But as in this problem it was given one thermal conductivity, then there is this given data is not used. If I use this critical value of thermal conductivity from data book, certainly this what is the necessity of this given data? So it was not used. So for using this data for as so certainly we will design the problem as per given input. So I want to use this given input also. Otherwise, this you can get it from literature also. So now I have critical temperature, critical pressure, critical value of thermal conductivity. Now out of this pressure, temperature and thermal conductivity, any two are given, so I can estimate third one. So here temperature and pressure was given, so I have estimated thermal conductivity. If say thermal conductivity and pressure is given, so I can estimate temperature. If say temperature and thermal conductivity is given, I can estimate the corresponding pressure. So exactly same we have followed for viscosity also. And now theory of thermal conductivity of gases for low density. Okay, so for monoatomic gases, this equation looks exactly similar. Okay, exactly similar. And if you rearrange this equation, so you can introduce the molar heat capacity at constant volume. Okay, molar heat capacity of constant volume. So thermal conductivity is 2 by 3 pi m kt d pi d square. So you can see here this is Boltzmann constant. Small k is a Boltzmann constant. D is the diameter of the molecule. So this is diameter of the molecule means oh, so you might have heard of this model of various molecules. So that effective diameter, so diameter of the molecule, because it is assumed in here all molecules are assumed spherical and interactions are very low. That is given low density. Molecules are far away, so interacting forces are negligible. And molecules are assumed to be spherical, and m is a mass of the molecule. What is the mass of the molecule? M stands for dimensions. L stands for dimensions in length, dimensions of mass. This is having a dimensions of mass. This is the having a dimensions of m, mass, length square, time, small t time, and capital time is temperature. T is the absolute temperature. Okay, T is the absolute temperature which will have dimensions of temperature, and Cv is a molar heat capacity which will have at constant volume, which will have dimension S square divided by T square, and K will be a thermal conductivity mLT. So this is the preliminary similar equation of Maxwell actually. So Maxwell equation in heat transfer you can call it as a. So again, so advanced Maxwell equation, advanced Maxwell equation is given by Chapman in heat transfer. So this is kind of you can say advanced version of Maxwell equation in heat transfer. It is given by Chapman. Again, when molecules are closer to each other, okay, closer to each other, the interacting forces will play a role. So interacting to estimate the magnitude of this interacting, so you need to go in details of statistical thermodynamics and molecular dynamics simulation. So all these parameters, okay, collision diameter, collision integral. So this comes from a molecular dynamics simulations and all. These are the parameters which are actually estimated by using simulations. So this collision diameter and collision integral, you can get it from data books, and using these equations, so you can get the this Chapman thermal conductivity for various monoatomic gases. This is true for monoatomic as well as polyatomic gases. and when density are comparatively not closer to liquid, but higher density, not closer to liquid. Okay, so for liquids and all, again these are, we are discussing the thermal conductivity of gases only. Okay, these empirical graphs is also related to most of the time, so it all depends upon critical temperature, critical pressure, critical actual temperature, actual pressure. So this equation is specifically used for gases. So here that the heading itself says that theory of thermal conductivity of gases at low density. At low density, this is derived specific purely from kinetic theory of gases. Using kinetic theory of gases, this is derived, while some input is taken from statistical thermodynamics and simulations. Okay, simulations done on molecular level. So, and correlation obtained in terms of this collision diameter and collision integral put together. This is the Chapman equation, which can be used for estimating thermal conductivity of gases. Now I can correlate the between viscosity and thermal conductivity. Okay, viscosity and thermal conductivity, I can have correlation because similar equations is available. What is the exact? So as we have done, so initially we were discussing heat transfer coefficient is similar to mass transfer is similar to momentum transfer coefficient. Now here also I got the equation for viscosity of gases. I got the equation for viscosity of the thermal conductivity, and these look similar. These look similar. In fact, the value of this sigma k is same. Okay, sigma k is same. Collision diameter is same. So this is same value I am using here. So I can correlate this equation. Okay. Now this is one equation I got. Okay, this is one equation I got, equation 1 and 2, and this is another equation I got. So I can correlate this. Both, this is Chapman equation, this is Maxwell equation. So here you can correlate what you will obtain. So divide one. So if I divide 1 by 2, so ratio of viscosity to thermal conductivity, what you will get in equation 3? Divide equation 1 by 2. So then rearrange the equation. Rearrange the equation. So this is what you will get. Okay, divide 1 by 2 and rearrange the equation. So it will be a thermal conductivity you can obtain from viscosity. Thermal conductivity of gases or monoatomic gases can be obtained from viscosity directly. If I have a specific volume, okay, specific volume. So if I have this so this specific molar heat capacity, okay, molar heat capacity at constant volume. Molar heat, not specific volume, molar heat capacity. CV is a molar heat capacity at constant volume. So if this is given molar heat capacity at constant volume and viscosity, so I can get the thermal conductivity of that gases. Now this is the derivative. This molar heat capacity at constant volume can be related with this gas constant. Okay, molar heat capacity at constant volume. Now substituting this here, so I can get the thermal conductivity using gas constant. 15 by 4 gas constant divided by mass of the gas, actually molecular weight of the gas multiplied by viscosity, and this will be rearranging this equation. Okay, and Cp, again Cp, these are the, these, if you go in thermodynamics, these are very well known studied. What is the molar heat capacity at constant volume, molar heat capacity at constant pressure, and substituting this, so I can get a K which is equals to Cp plus 5 by 4 R by M into viscosity. This is called as the Ekman equation. This is true. This is also true for polyatomic gases and monoatomic gases also. But most of the time for polyatomic gases, this equation is used. Most of the time monoatomic gases, this equation is used. So even if you use this for polyatomic gases, you will get some error, but you will get a close value. This will be more correct for polyatomic gases. Is it okay? Okay, we'll continue in next class. If you have any confusion over today's discussion, you can stay back. Otherwise, join in next class.